just wanted to do a quick reminder of the anatomy of a neuron. So here at the end of the neuron we have the dendrites. So these are what receive the signal, and once the neuron has received the signal, it goes into the soma, or the cell body, and this is what tells the neuron when there's enough signal to fire an action potential. So once it fires the action potential, the signal travels down this part, which is the axon, and then once it reaches the end of the neuron, it leaves through the axon terminal down here.
So guys, before we talked about what a neuron is, and we briefly introduced the idea of action potential. But now we're going to go into more information about what exactly an action potential is. So, an action potential is an electrical impulse that delivers information between neurons. So, during an action potential, there are different channels along the axon. And in these channels, sodium is able to flow into the axon, and potassium is able to flow out. Additionally, the positive charge on the sodium allows the positive charge to move down the axon, which allows additional channels to open.
Briefly introduce the topic of the action potential. And one way that you can visualize an action potential is to measure the change in charge outside of the cell. And so for one neuron, you would end up getting a graph with time down here, and then this would measure the change in charge. And so as you get a high enough change in charge, you would get an action potential. And it's important to note that all of the action potentials are the same peak height. And this is because an action potential is an all or nothing response, meaning that if you don't get the necessary charge difference needed, then you won't see an action potential, and that if you get that charge difference, then it will be the same the all response. And so in order to strengthen the signal, you can look at a setup where you're looking at multiple neurons. So in this case, you should have 3 different neurons. And then on the graph, you would get what we call a compound action potential. And so for the compound action potential, the peak height would be a combination of the first peak, or the peak heights of all the individual neurons added together.
We just talked about what can affect the strength of an action potential, and we said that the strength is always constant because it's an all or nothing event. But now we're going to look at what can affect the speed of an action potential, and this can actually change. So the biggest thing that changes the speed of the action potential is something called myelin that wraps around the axon. And so myelin is basically just more layers of cell membrane wrapped around the axon, and it acts as an insulator and keeps the charge inside the axon traveling down. And so when myelin is present, charge can travel faster and further down the cell, or down the axon, because it won't be leaking out. And then we have these spaces here between the myelin, and that's where we have the sodium and potassium channels, so ions can keep flowing in. And then there are a few other things that can affect the speed of an action potential, such as the diameter of the axon. So as the diameter increases, the speed will also increase. And then temperature is another thing that will affect the speed, but you guys will look into that with your earthworm action potential lab.
Alright guys, so now we're going to talk about conduction velocity. Conduction velocity is the speed at which the action potential can move through the neuron. And this is something that we want to be very quick. We want this to be quick because, for example, if you're walking along and you step on a stapler and the conduction velocity isn't quick and you keep your foot there, your brain is not going to know that it hurts. So if the conduction velocity is quick, you should be like, oh, ow, that hurts, and move your foot before you get hurt.
So to measure the velocity of an action potential, we'll measure it just like we measure any other velocity. So we'll divide the distance traveled by the time taken to travel. And so for this experiment, we're using 2 different electrodes. So we'll measure the distance between those 2 electrodes, and then we'll measure the time that it takes to get from one electrode to the need two electrodes, because if you just have one, you would only know when the electrode or when the action potential passed that electrode, but not how fast it passed. So now if we divide the distance between the two by the time it takes to get from one to the next, we'll know the velocity of the action potential.
Alright guys, so today we will be talking about a Faraday's cage. A Faraday's cage is made out of conducting material, like you can see right here in this picture. And additionally, you will see these two cords, which are used to ground the cage. Usually the cage is grounded to a computer, but you can see what your cage will be grounded to on your worksheet. We use the Faraday's cage, so when we record the action potentials of the worm, we are only recording the action potential of the worm instead of the action potential and all the electrical fields that are in the environment. If you want, you can try to record the action potential without the cage and you can see what happens.
Okay, so in lab you'll be doing an experiment with earthworms, and so we wanted to tell you a little bit about the anatomy of an earthworm. So here's just a basic picture, and this here is the posterior end, and this is the anterior end of the earthworm. And so an earthworm has three main neurons, so one medial giant neuron, and then two lateral giant neurons. And this picture just kind of shows where they all come together right here. And so this just shows a little better the relationship. And so the medial giant neuron is in the center that receives information from the anterior end of the worm, and then you have the lateral giant neurons on either side, which receives information from the posterior end. It's also important to note that the medial giant neuron is slightly bigger than the lateral. And so earlier we talked about myelin, and so an earthworm's axons are myelinated. And so this is showing the comparison between the axon size and the myelin thickness with the earthworm. So here you can see that as the axon diameter increases, the velocity also increases, and that the same is true for as the myelin thickness increases, the velocity also increases. Looking at that a little further and graphing it, the conduction velocity is proportional to the square root of the axon diameter, and that the conduction velocity and the myelin thickness have a linear relationship as shown here. And so that tells you a little bit about the earthworm, and you will find out more in your lab.